Hi everyone. So we're going to pick up where we left off yesterday with those two example problems. It looks like we really struggled with the first example problem, but we all pretty much got it on the second example problem. So I'm going to start with the one with our copper fluoride. Okay, so for part A, it tells me that I have this 0.01 molar copper nitrate. Okay, so I'm going to be using that copper nitrate as my source of copper ions here. So first I'm going to set up my equilibrium. Between my solid and my ions, make my rice table. I remember that I don't include solids in this rice table. So that copper nitrate is going to provide all those copper ions. And since there's one copper ion for every copper nitrate that I have, if I have 0.01 molar copper nitrate, I really have 0.01 molar copper ions. And no fluoride ions are being provided from this. My changes, I'm going to lose x here. I'm going to add x here, and I'm going to add 2x here because of my stoichiometry. So I'll have 0.01 plus x and 2x here. But if I look at this KSP value, my KSP is 3.9 times 10 to the minus 11, which is a really small KSP value. So this plus x right here is negligible. Okay, so my KSP is really equal to 0.01 times 2x squared. Okay, so when I solve for my x here, my x comes out to 3.1 times 10 to the minus 5. Okay, and that's going to be molar CuF2. So remember, I'm solving for that molar solubility here. Okay, so that should have been my answer for part A, was this 3.1 times 10 to the minus 5 molar. For part B, and now I'm looking at having a solution that's 0.01 molar in NaF. So the common ion that's going to be provided here is that fluoride ion. So again, I'll write my equation here, my equilibrium equation between my ions and my solid. I'll write out my rice table. I'll remember that solids are not included in my rice tables. Now I start with no copper ions, and everything that I start with is from that NaF. And since in NaF there's 1 mole of F minus ions for every 1 mole of NaF, that 0.01 molar NaF is 0.01 molar in fluoride ions. I'm going to have that same change as before. So for my equilibrium concentrations, I end up with x and 0.01 plus 2x. But again, my KSP value is really, really, really small. Okay, I've got this 3.9 times 10 to the minus 11. That means that this change is going to be negligible. So I really have x times 0.01 squared. So when I solve for my x this time, I should get 3.9 times 10 to the minus 7. And again, since I'm solving for that molar solubility, it's molar CuF2. So that should have been my answer for part 2. Then for my second question, okay, this is the one that we seem to do a little bit better with, the word problem rather than the math problem here. So I have my MgOH2 solid in equilibrium with the Mg2 plus ions and 2 OH minus ions. And the first question asks me, how does the addition of OH minus from a base affect the solubility? So if I add OH minus, that's analogous to increasing this OH minus right here. And I always shift away from that increase, which means that I'm going to favor the reverse reaction, and I'm going to be making more solid. And more solid, less dissolved ions means I decrease the solubility here. So for part A, the addition of that OH minus ion would decrease the solubility. If instead I added H plus ions, like in part B, well, those H plus ions are going to react with the OH minus ions here to form water. We know H plus OH minus will make H2O. So that's really like I'm decreasing the amount of OH here. I'm taking OH minus ions out of my solution. I need to shift towards that decrease so I can make more of those OH minus ions. So I'll shift to favor the forward reaction, which means I'll have less solid and more aqueous ions. So this will increase my solubility here. So those were the two example problems that we left off on. Let's switch back to the PowerPoint. And we should have left off on this slide over here. okay, where we're now going to talk about precipitation. Okay, so when I'm talking about precipitation, I'm not talking about the precipitation that falls from the sky like snow or rain. We're talking about precipitating a solid out of a mixture of aqueous solutions. So if I mix two solutions together of BaCl2 and Na2SO4, I should form a precipitate here. The net ionic reaction would show me that I'm forming this solid, oh, I'm sorry about that. I'm forming this solid of BaSO4 because we know that that's insoluble, and I call that my precipitate. If I wanted to find the Q here for this reaction, this net ionic reaction right here, I would have the concentration of Ba2 plus ions times the concentration of SO4 2 minus ions when I end up with this equilibrium, just like when we found my K here. So in a precipitation reaction, in my solution, if my Q is equal to my KSP, the system's at equilibrium, and that tells me it's a saturated solution because I only end up with this equilibrium system between my dissolved substance and my solid if I have a saturated solution. If my Q is less than my KSP value, that means more solid needs to dissolve to get Q equal to KSP. So no precipitation happens there, I actually dissolve more of the solid. If my Q is greater than my KSP, that means that I need to get rid of some of those aqueous ions and turn them into the solid. So the salt will precipitate out of solution until my Q equals my KSP. So knowing that, we have another practice problem here that I would like you to try to solve. You need to solve for your Q value here for your precipitate, and you need to compare that to your KSP to see if a precipitate will form. So take a second, solve it, and put your answer when prompted. All right, so if we're trying to solve this problem right here, first thing I'm going to do is I'm going to get to my equation here, and I'm going to figure out what precipitate will form. So if I'm mixing together Na2SO4 and PbNO3 I should see that I'm going to form NaNO3, balance it out, 2 of those, plus PbSO4. I know that this NaNO3 is going to be soluble, so my precipitate is this PbSO4. So if I'm talking about this KSP here, or this Q, I'm talking about this equilibrium between the PbSO4 solid and the Pb2 plus ions and the SO4 2 minus ions. So to calculate my Q here, it's going to be equal to the concentration of Pb2 plus ions times the concentration of SO4 2 minus ions. Okay, so I need to get those concentrations. Okay, I'm given molarities, but I'm given molarities for my initial aqueous solutions, not for my individual ions. So I have to figure out what the molarities are of those individual ions here. Okay, so it's telling me that I have 0.1 liters of my PbNO3 Okay, so I'm going to get that to moles first. Okay, and it tells me my molarity is 8 times 10 to the third molar. So that means 8 times 10 to the third moles per liter. And that's going to give me 8 times 10 to the minus 4 moles of Pb2 plus. Okay, I'm going to do the same thing for my Na2SO4, looking at my SO4 2 minus. So I've got 0.4 liters of this Na2SO4. I'm going to get that to moles. It tells me the molarity is 5 times 10 to the minus 3. So that's moles in 1 liter. And it gets me this 4 times 10 to the minus 3. Oh, wait, no, I'm sorry. That's the wrong number. I was looking at the wrong thing. Sorry. That should give me 2 times 10 to the minus 3 moles of SO4 2 minus. I didn't have to multiply by any other numbers here because if we look at my formulas, it's 1 Pb2 plus ion for every 1 PbNO3 and 1 SO4 2 minus ion for every 1 Na2SO4. Okay, so now that I have my moles, I'm mixing these two solutions together. So to figure out the molarity of these ions, I need to add the volumes together. So I'm mixing 0.4 liters with 0.1 liters. These are additive volumes here. So my total volume is 0.5 liters. So to get these to molarity for each, I need to divide both of my moles by this 0.5 liters. So when I do that, my molarity of my Pb2 plus should come out to 1.6 times 10 to the minus 3 molar. And my molarity of SO42 minus should come out to 4.0 times 10 to the minus 3 molar. Again, how I got those was I took the moles that I calculated before and divided them by that additive volume of 0.5 liters. So now I plug these in to solve for Q. And Q should then come out to 6.4 times 10 to the minus 6. My KSP we know was 6.4 times 10 to the minus 7. So when I compare those, my Q is larger than my KSP. That means I have too many ions and I need to get rid of some of those ions and turn them into solid. So a precipitate will occur here because my Q is larger than my KSP. Hopefully we were all able to figure that out. Okay, so oftentimes in lab what we'll need to do is selectively precipitate an ion from a solution. So ions can be separated based on their salt solubilities. A reagent is used usually that will precipitate one or more ions here. So for example, if I have a solution that contains both Ag plus and Cu2 plus ions, and I add HCl to it, well, the KSP of AgCl is 1.8 times 10 to the minus 10, while the KSP of CuCl2 is very large. That's a very soluble compound. I know that AgCl is not very soluble, but that CuCl2 is very, very soluble. So the AgCl will precipitate out of solution, and I can filter it out to separate these two cations here. So that would be selectively precipitating the Ag based on its solubility when it's in a compound with Cl, as opposed to Cu2+, which has a very high solubility when it's in that compound with Cl. Okay, so again, if I wanted to precipitate out the Cu, I had a solution containing copper, zinc, and hydrogen ions. Okay, I add this H2S to it, and I know that that sulfur will precipitate out with copper and make this CuS. I can selectively remove that. Okay? And then after that CuS is removed, I'll increase my pH, and that will allow my ZnS to react, and I can remove that ZnS. Okay, so I can use differences in solubilities to precipitate out. We know the solubility rules, but this is a little chart that will tell me how I can actually precipitate them out. You don't need to memorize this chart. You should already know your solubility rules, and that should help you there. So one thing that we talked about was Gibbs free energy. Now we didn't get into the bulk of Gibbs free energy because that's Unit 9. I'm going to talk about it a little bit just to cover anything that might be on the AP exam with it, but we'll learn more about this Gibbs free energy a little bit later in the year. So remember, Gibbs free energy is the amount of free energy available for a reaction to occur. So my equilibrium constant is related to temperature and the difference in Gibbs free energy between reactants and products. That will tell me what this equilibrium constant is. The magnitude of that equilibrium constant specifies the relative proportion of my reactants and products at equilibrium. So the higher that equilibrium constant value, the more products I have, which means the more spontaneous that forward reaction is. And remember, a spontaneous reaction will have a negative Gibbs free energy, a negative delta G value. That's going to be spontaneous. So the bigger that Kc value, the more negative that delta G value is because I have more of these products. And I do have an equation that can relate the two. Okay, so if I look, equilibrium is based upon my delta G. Okay, so if I have my delta G, it's equal to my standard delta G plus R times T, that gas law constant, times T. And for my gas law constant, I have to use my 8.314 because I'm talking about delta G, so I'm talking about joules. So that gas law constant times the temperature in Kelvin times the ln of Q, the natural log of Q, that reaction quotient. If I'm at standard conditions, my ln of Q equals 0 because remember, this degree symbol right here stands for standard. Okay, so that ln of Q will equal 0. So delta G will equal delta G standard. And at equilibrium, that delta G standard equals negative RT times the ln of K, because at equilibrium, Q equals K. So I believe this equation is on your reference table. You can check that though, that delta G equals the negative RT times ln of K. And that's going to relate my Gibbs free energy to my equilibrium constant. Okay, so that's everything from Unit 7. I'm going to be posting, or what should already be posted, is an AP Classroom assignment that is FRQ based for reviewing this Unit 7 equilibrium stuff. Okay, so your next part of this assignment is to go on to AP Classroom and complete those FRQ questions. You can type in your answers. For some of them, I think you have the option of handwriting and uploading a file, and then I will grade them, and I'll have a video dedicated to going over those questions next week.